Today, from interning at Google to hacking Kafka streams, this is Confluent Developer.
We had a customer who joined us in the early days, and they basically were experiencing, the kind of unbound growth that a startup, with a lot of AI customers might see.
I'm going to ask you what the hardest problem is you've worked on. Is this the one?
Right.
Okay.
So
No, that's
growing fast.
That's scary.
Yeah, exactly. Scary. That's the right word.
Hello there, everyone. I'm Tim Berglund, and welcome to Confluent Developer, where we explore the fascinating journeys of software developers tackling complex problems. In this episode, I'm interviewing my friend Sophie Blee Goldman. From her start as an intern at Google working on container orchestration to becoming a well-known figure in the Kafka community, Sophie shares a story of the time she and her team hacked Kafka streams in a really creative way to make it easier to scale in the face of Kafka partitioning limits. Now, there's plenty of Kafka and Kafka streams inside baseball in this episode, but Sophie really takes us deep into her solution, and I think she does a fantastic job explaining it all. Let's get to it. Sophie, welcome to the Confluent Developer Podcast.
Yeah, thanks for having me.
Yeah, it's good to see you again.
You too.
All right. For whoever doesn't know you, what do you do? Who are you?
Fair question. Yeah. My name is Sophie Blee Goldman. Some people might know me from Kafka community, the Kafka streams world. Other people, I used to work here at Confluent. And currently, I'm a software engineer at my current company, which is Responsive.
Responsive. What do you do there?
Software
engineer. What do you work on?
Yeah, that's a fair question. Interesting question. So we're currently in the middle of a pivot, and I don't want to give away all the exciting details just yet. I'll tease people and say they can go to responsive.dev to sign up for a mailing list to get news and notifications. For now, I'll just say we're pivoting to something in the observability space.
Okay.
We have a good team that's built a lot of deep infrastructure and has a lot of experience in that. And as a startup, we're kind of always on the lookout for what's the exciting new opportunity where we can really have the most impact. And we think we found something. So we're currently changing directions. But previously, before that, we had a Kafka Streams platform, and we're still all in favor of Kafka Streams. Still love it as a technology,
yes,
even if that's not our current focus right now.
All right, awesome. I look forward to hearing more about that. What was your first job before you were a software engineer and a prominent person in the Kafka world? What was your first job?
Fair question, I guess. So my first job that I was paid was under the table, working for my mom in her dean's office, sorting papers. Not too exciting, but I guess
you were paid by your mom or by the?
But
okay.
Keep that quiet.
No, we know nothing.
Yeah, this is not a public space, right?
Yeah, it is the internet, but.
So yeah, my first above board job, I guess was my internship at Google. I know, the classic tale of every software engineer. A little embarrassing to look back, but no, it was a good time. They spoiled their interns, which is exciting as an intern and a little bit embarrassing looking back, but it was a good time. I was a little bit isolated from most of the interns. I was up in, I think it's called Crittenden, the area. It's like way off the normal Google campus. You have to take a bus to get there. It's kind of near the LinkedIn campus or where it was.
Okay, but it's in the Bay Area.
Yes, yeah, okay. It was in the Mountain View campus. But yeah, that's where they stuck all the infrastructure folks. So all the deep nerds of the nerds, they sent them up the hill to live alone and work on Docker and containers and all those fun things.
Nice. Yeah. People external to our world don't understand. There is a hierarchy of nerds, and infrastructure is pretty high or low depending on which way you're sorting in that ordering. What kind of stuff are you working on?
Yeah, so they really thrust me into the deep end as an intern. I must have been like 19 at the time or so, and I was working on containers, container migration, the system Borg at the time, which basically is the precursor to Kubernetes. All exciting stuff that I think looking back I probably didn't really understand fully at the time, but it was very exciting. I was there when they were planning their DockerCon, which just seemed like a big deal in a whole new world, which I'm sure was very exciting, even though I didn't get to go to it.
Yeah. And is now. That's a major event now.
Yeah, exactly. Yeah. So I got to see there when it was just first getting started, I guess.
That's kind of cool. And I guess that was a time when Docker was established, like, okay, this is how we're going to do containers, but how are we going to orchestrate containers? There was really a struggle for control of that.
Exactly.
That world.
And that, I think probably at the time, Kubernetes was at least not in my vocabulary, if in anyone's.
No, it was not clear at that point how that was going to go. And there were things like Mesos and like what kind of approach are we going to take to this? And I think the judgment of history is that Kubernetes won.
Yeah, that seems to be the case.
Yes. Non-controversial take there.
It is weird to look back on what it was like before. And it was, it was all kind of a mess. There was a lot of different thoughts in the area. I specifically was working on something called container migration. And it was actually an open source project, which is interesting. I have history with open source projects, I guess. It was called CRIU, so the acronym CRIU. It's been in container something with an R, container something with an R, in user space. And basically, you know what, I'm sure. No,
go on. And so I'm going to ask you what the hardest problem is you've worked on. Is this the one?
No, probably not.
Okay.
I mean, this was hard in a different way. So this was interesting. Maybe the technological details were not that interesting of it.
Right.
But it was a weird dynamic because I was at Google on the basically the Docker team, the infrastructure team, working on an open source project with the major contributors being in Russia. So
okay.
Setting aside current politics, this was 5, 10 something years ago.
Yeah, they're different geopolitical.
Yeah. But still, there's a time difference, right? And so, it was very hard to make progress as an intern when you're having these open source discussions, which, tend to drag on a lot more, and there's a lot more bike shedding on any open source project than compared to, how move fast, break things companies tend to be on the inside. So anyways, there was an interesting dynamic where in the open source side of the project, we were having these long back and forth discussions over every PR, every proposal, with people that were, basically a full time zone ahead of us. So every single conversation had a relay time of 24 hours.
Right.
Which was a struggle. And I think in the end, we kind of had to drop any sense of real progress on the open source side, and Google had its own internal fork where we merged things. And I guess once the interns left, then they would clean up the mess. Or I'm not really sure what happened after we left.
Yeah,
but all I know is a lot more of my PRs were merged into the fork internally to Google than the open source project. And so sometimes you can only make progress on the inside.
Yeah, they move forward to their fork. Because, collaboration across time zones and agendas and motivations and incentives and everything is actually hard to do.
It is.
And PRs are magical, but they don't make it so that people all think the same thing.
No, that is very true.
Yeah. Have you ever been in a PR? So, in your career so far, most interesting problem you solved? What do you think?
Yeah, so there's a little bit of a tie-in to the last thing in terms of kind of managing expectations and realities around open source projects. But I'll start with the backstory.
Okay.
Probably the most interesting challenge that I had was at Responsive when we were still working on our Kafka Streams platform. We had a customer who, they joined us in the early days, and they basically were experiencing, the kind of unbound growth that a startup, with a lot of AI customers might see, right?
Okay,
As you can imagine. And so their Kafka Streams application, which was running on our platform, was, of course, constantly growing in its needs in terms of resources and throughput. And for those who don't know, with Kafka, everything is divided up into partitions, just to give a quick little overview. And the partitions are basically the maximum limit that you can have on the parallelism. And those partitions derive from the consumer groups, and Kafka Streams derives from the consumer groups. And so basically with Kafka Streams, the most you can scale out is limited by the number of partitions that you have in your upstream topics.
So for the non-Kafka folks listening, if you've got, say, five partitions in a topic, the topic is like a big log, and you split it into 5 partitions, you can have 5 processes doing the compute on that. You can't have 6.
Right.
You can have 5.
You can have 6, but it'll sit there and it won't have anything to do.
Until KIP 932. But that's not what this podcast is about.
Yes.
Keep going.
Right. Well, it is, as you can see, it's a kind of a fundamental problem. And so a lot of work in Kafka has been done around how to solve this problem. The issue being that, once you create a topic, the partitions, are set in stone. So,
yes.
You don't want to over partition because you're wasting a lot of resources perhaps up front. But if you under partition, then you're going to hit this maximum limit down the road.
And you can change it. It's just that you'd rather not. It's not a great way. It's not a great way to live.
Very complicated, which maybe will be saved for another podcast. I'll let somebody else deal with that.
Yes.
So interestingly, actually, this customer that we were working with, they had already increased the number of partitions, but it was a huge ordeal, and it's not something that they wanted to do again. And so as they were growing and growing, they were kind of coming up. We could predict and project outwards. At what point is their Kafka Streams application going to be unable to keep up with the throughput, given the number of partitions and the number of processes that can actually be doing active work?
Biggest instance you're sort of willing to field to execute one of those processes, boop, boop, there's your limit. You're going to run out of gas in 30 minutes or whatever.
Yeah, exactly. Luckily, we had more than 30 minutes, but we were something on the timeline of like a month. Right.
Okay.
So
no, that's
going fast.
That's scary.
Yeah, exactly. Scary. That's the right word. Exciting but scary. Like all challenging problems start out. But yeah, so we had this problem. We had pretty much a hard deadline approaching, and like the horizon of about a month. And we were trying to solve this problem with fundamentally a platform that was on top of open source Kafka Streams. So we didn't have our own fork. Unlike Google, we didn't have our own fork of Kafka Streams.
Right.
We built something on top of and around Kafka Streams that plugged into the actual open source code rather than replacing it or anything like that. So the struggle there is that we were really beholden to what was in open source Kafka Streams and what could be in open source Kafka Streams.
Right, because you at this point have not forked.
Right.
That would be a big decision to do.
Yes.
That could affect kind of your go-to-market and like adoption, and it's a fork of Kafka Streams. I don't want to, big deal. You don't want that. Now, a quick word from our sponsor. Confluent Developer, the podcast, is brought to you by Confluent Developer, the website, which has everything you need as a developer of data streaming systems. And it's completely free. We've got curriculum, hands-on exercises, executable tutorials, the online data streaming engineer certification, also free, a way to find a meetup near you, those are free. Everything is there. I really want you to be successful in your journey as a data streaming engineer, and this is the site that has what you need. Check it out at developer.confluent.io. That's developer.confluent.io. Now back to the show.
And especially because our clients were, really these were applications that were running in their environment, so it wasn't the same as like Google internally using their own fork. This would be asking our customers to use a fork of Kafka Streams, which is a whole other
to build against some new dependency and redeploy.
Right. Yeah.
That's mean.
Big hassle. Yeah. So that was really kind of off the table.
Okay.
But there wasn't really this limit of partitioning and maximum parallelism is really like a fundamental limit in Kafka Streams, which derives from the limit of the partitions in Kafka.
Yes.
So there wasn't at least an obvious thing that we could sort of build on top of it that would necessarily help. But of course, the problem is, I'm a committer in the Kafka Streams, which means like we could have done we could have contributed code to Kafka Streams, right? And that was it's naturally our way of thinking. We're working with an open source project. We want to do something that will be beneficial to everyone. But the problem was this 1 month time limit.
Yeah, I was going to say, like you learned in that internship, coordinating that kind of change amongst an open source community, many of whom sort of don't care about your problem, right? They got on the motivations. That's tight. I don't see that happening.
Yeah, I mean, and the reality was like this was a dearly needed feature for Kafka Streams, and I'll get to what this feature is, of course. But no matter even if you have everyone on board with the direction of a proposal, there's just like the realities of the open source project itself, which is there's a process, right? So you have to draft a proposal, a KIP, Kafka Improvement Proposal. You have to publish that. It has to go through discussion and basically have the entire community agree on it, line by line, without any little like single sentence of conflict, and then vote for 3 days. And that whole process, that's usually weeks to months in itself.
Yeah.
Even for something that's rushed, even for little projects sometimes can take a long time. And for big ones especially, even if everyone agrees that it's a necessary improvement, how exactly to approach it is always going to be something that just takes a while to hammer out.
Because you've got this consensus mechanism, you don't have a unitary executive who can say, this is the thing we're doing. That's not how Apache projects are governed.
Yep.
They're governed by the consensus of a group. Always slower to make decisions that way. Not worse, but it's definitely slower.
Yeah.
And you had a month.
Yep. Yeah.
Ish.
It makes for high quality code, but when you're kind of looking at, down the barrel of the gun with this 1 month deadline, that really, unfortunately, wasn't an option. Okay. So now we're at these crossroads where, we can't or we won't fork the project. We can't fix the thing on time by going through open source Kafka. So we really had to find a way to fix this with our wrapper, our platform that was built on top of open source Kafka. Mm-hmm. But the problem there is that the thing we're fixing is really the fundamental architecture of how Kafka Streams works, which is that you have a thread, a stream thread, which is assigned the partitions of the Kafka topic, mm-hmm. and that's how all the work is done. So really we were talking about kind of rewriting the threading model of how Kafka Streams works in order to be able to work on a partition in parallel with multiple threads, which is kind of hard to do from outside of a project, as you can imagine.
Yes.
So that was the real challenge. Kind of came down to how do we fiddle with the way that threads are used and operated and managed in Kafka Streams without changing Kafka Streams itself.
And by default, that pool of threads is not the same as the number of partitions. You've got number of partitions and your maximum number of processes you can scale. Number of threads is within one of those processes, and they're different things.
Yeah. So usually, with people that have, correctly allocated their resources and, don't have a lot of unforeseen growth, you might have one stream thread which could be processing multiple partitions. But in the default Kafka Streams, you can't have one thread, multiple threads working on one partition.
One partition, yeah, that's not how it works.
Yeah, just as the general rule of, parallelism and concurrency.
Ordering, all the assumptions that everything in Kafka makes is just,
exactly.
It's just a no.
That's a big one, Everything in Kafka it's a log, so everything is by definition in order, and all the processes are built on top of that. For example, correctness, processing guarantees, exactly once, they are built on this assumption that records are processed in a partition in order, and they're committed in order, and they're flushed in order, and all the stuff that comes out of that. Not to mention trying to, write to state stores or, forward records that are being executed in parallel and all the other concurrency issues that arise from that.
Right. And as an aside, at the time of this recording, there's this big news of a thing that's in preview in Kafka 4.1 that you know about it, but audience might not, that is a mechanism to get around that. If you need multiple processes consuming from a single partition, more like a classical queuing system, there's this new way to do that. It's called Queues for Kafka, KIP 932, if I'm getting that number right. And it's all this extra stuff that's taken years and a big KIP and lots of work and investment, and that's not going to happen in a month.
Yeah, and that was a big deal, and that was just for kind of plain Kafka and not for Kafka Streams.
Not even for Kafka Streams, right.
Exactly. So, we had to figure out something to do that we would be basically kind of injecting a solution into Kafka Streams from the outside. So how do we do that? Basically, we ended up writing a wrapper. We kind of used our few access points. We looked at the API that Kafka Streams offers, and we thought, where can we actually inject something into Kafka Streams?
What can you hook?
What can we do? Exactly. Yeah. And so the main API of Kafka Streams is you write your application, you write basically what the processing topology is, which is just how our record is actually being processed.
Yeah, get stuff from here, do things to them, and put them somewhere.
Basically, yeah. You can think of it as like a graph, and the records just flow through the graph. Call it the topology a graph all the time. So it's the best way to visualize it. And you write some code to define the individual nodes in that graph, and then you just write the actual application, which your application is calling things like start and stop. But there's not much going on in the application layer.
You define your topology, which feels like the code that you're actually writing, but the execution-wise, you've just handed off some data structures to this engine, and then you call start.
Yep, basically. And once you call start, that's when all the magic happens. Kafka Streams, it creates its threads. Those spin off and operate separately. and your sort of main application process. People do different things, but usually the main application thread is just kind of sitting there and waiting for Kafka streams to trigger a shutdown or something like that.
Yeah.
Not much going on there. So we really had to look at like the stream threads. How could we kind of get into the stream threads and hijack them, for lack of a better word, to do what we want? And really, the best way, or perhaps the only way to do that, was going in through the processor topology.
Okay.
So what the stream threads do is, each stream thread, it gets its task. Essentially, it's assignment of a partition corresponding to the input topic, and it grabs records from that partition, and then it executes these graph nodes, these processors that the user has defined. So we thought, well, a good way to get control over the stream thread is when the stream thread is actually executing these processors.
Okay.
So.
And the processors are things, if I'm using the API that says filter and group and things like that, those are creating processors. There's a graph of these, records are flowing through the graph, and the processor gets a record, does stuff with it, puts it to its output.
Yeah, kind of most simply, a processor is just, it's an interface, and it has an open and a close, basically, methods, but one important method, which is just process, which just takes it a record and it...
Little life cycle, and now do your thing.
Processor has a process method. I know, it's crazy.
It's hard to name things, and it seems like that was a win.
Oh yeah, we had to create a new processor API to fix some problems, and we just couldn't think of a better word than processor. So we had to change the whole package and structure and everything so we could maintain compatibility.
Keep processor in this other package. Yeah.
Yep, exactly. Okay. It's just too perfect of a term.
I actually kind of hate that, but
well, it was
it worked. Yeah,
that was a controversial kip.
Which processor is this? Well, it's yeah.
I won't say it didn't cause any problems.
Say hello to fully qualified class names.
The word processor was hard to give up.
It's too good.
It's processing.
It's too good.
Yeah, and so it's processing. It processes these records, and that's when the stream thread is doing its thing. The stream thread calls, grabs a record. It calls process on the first process, and then processor, and then they kind of define how it percolates through the graph. But basically, it's just calling process a bunch of times.
Okay.
So we thought, well, we can just inject our own implementation of a processor using the processor API, basically how you define a topology, and that's going to put a wrapper around the user's processor. So basically, we have this little window, this little moment of time between when the stream thread is picking up a record from the partition and handing it to the user processor. Mm-hmm. We tear open a little hole and we injected our code right there, right before the user's processor is invoked, and that's kind of how we got control over the stream thread. So that's in some sense that was the hard part, but that's also just where it all begins. After that came all the actual challenging coding. But at a high level, what we did was gave each stream thread its own separate thread pool that it could use for the actual execution of these methods. Oh. So rather than the stream thread just forwarding the record to the user processor, it would actually stick it on a queue, and then move on to the next record without calling process at all.
Okay.
And then the thread pool, we have a set number of threads. They're just sitting there. They're picking up records off this queue, and they're the ones calling the actual process method. Yeah, okay. Exactly. And they're doing that in a loop.
And backing up, this lets you have more of those threads in that secondary thread pool than you had partitions.
Yes,
because you're not going to have more Kafka stream threads than you're going to have partitions. But if you have, I'm going to guess, more cores on the instance than that, this is how you use those cores.
Exactly.
That second pool of threads.
Okay. Or even at the kind of the limits, you might have one instance with an instance, a process of Kafka streams for every partition, in which case you would have only one stream thread on that instance, and they're, generally most modern machines have more than one core. So there's a lot of work that's kind of being neglected or picked up. So the idea that, the high level idea here is really, well, let's get multiple threads working on one partition at the same time, rather than each thread being responsible for iterating over every record in order for the partition. So
right.
It's basically
at this
processing.
limit, you're compute bound. I mean, that's the whole.
Yep.
That's how this whole surprisingly dramatic story started. I mean, you've got me. I'm like, okay, how are you going to do that? And I kind of get your solution with just listening to you without seeing code. That makes sense.
Yeah, I mean, that's kind of how we came to it, right? It's just you talk through the problem and eventually it starts to take shape.
So what happened?
Yeah, well, so I'll cut the drama short, and I'll just say that in the end it did work out. We did not manage to run up against this throughput limit and crash and have to hang our heads in shame or anything like that.
Excellent.
But it was a lot of work, and there were a lot of interesting technical challenges there. I did a talk on it actually at I think the Kafka Summit London 2025. So if anyone is more interested on the technical details, I'll refer them there. So
I should have known that, and I'm just going to confess to the audience. I didn't know that, but link in the show notes.
All right, yeah, there you go. And the code is it's up. Anyone can take a look at it if they want to. They can try it out. And yeah, we call it our async processor. I know there's some controversy over the name, as certain other entities think it should be called a parallel processor.
Yeah. Okay.
Which because it is doing parallel processing, but the way that it does that is by processing these records asynchronously.
Yes.
Within a partition.
Yes.
So we don't have to get into any bike shedding over the names. We'll leave that for the KIP discussions. But
absolutely, we do not. But I'm just like in my mind, I'm going, well, okay, yeah, I get why they're mad because there's threads, and if it was async, there'd be one. But I am literally doing that in my head right now. I'm going to stop because it's fine. Like we said, we had the biggest naming win in the world with processor, and they can't all be like that.
Exactly. I mean, we still stand by our async processor,
100%.
but I will acknowledge that to some people, they might wonder why it's called that, and it's because each thread is processing asynchronously these records.
And I got to take you back into there for a second because I'm thinking of something. Is there an ordering problem in there, your queue?
Well, I mean, no, that is a good question.
Yeah.
So yes, I mean, there's fundamentally, like, it all comes down to ordering. That's how correctness, that's how processing guarantees, all those good things are guaranteed. And there's kind of like one key observation that we made that is generally applicable, even if it might not fit every single case. But usually you have a partition which includes records of many different keys. So you might have, letters in your key, A, D, G, whatever. They all map to partition 1.
Yeah.
So you have multiple keys.
Big set of keys will map to a single partition.
Yep. You'll have a few different keys in your partition, or many of them. And fundamentally, you only really care about setting aside, things like committing and the Kafka mechanisms that rely on ordering for a second. We'll come back to those. But in terms of correctness, you only really care about maintaining ordering within a key, right? So let's say you're like processing computing the number of times each letter appears in some document. Yeah. It doesn't really matter if you process the counts for D, for let's say the E and the before you process the T, because they're tracked individually. And
as long as all of the E's are in the order that the E's arrived.
Exactly.
It's okay if they interleave with the H's.
Yeah. So, you don't
have a guarantee about those.
Exactly. The insight there really is just that, Kafka partitioning kind of gives a natural way to break up and maintain and track things within a single Kafka topic. It's not sort of the fundamental limit of parallelism. It's a physical limit because of Kafka, but in terms of the theoretical limit of what can be processed within a topic or within a partition, it's really the maximum limit is set by the number of keys that you have, the number of distinct keys.
Okay.
And so that's what we are really trying to hit, is to be able to scale up to handle, potentially up to the number of keys in terms of your parallelism, rather than being bound by the number of partitions.
Okay. No, that makes sense. So depending on the cardinality of the keys and threads in the instance, cores in the instance, that could get very exciting. I see how it all fits together.
Yeah. So our little innocent little queue was not just a simple, first in, first out kind of thing. It really, what it did was tracked separate queue for each key that we saw. So in that way, we made sure that records could be pulled from any of the non-blocked keys. In other words, if a thread is looking to pick up the next record, if another thread is currently processing, something with the letter E as the key, another thread can't pick up and process something else with the letter E, because then those would conflict. There would be ordering issues. There might be issues when they tried to, if they tried to write to the state store at the same time or read from the state store at the same time. You can kind of imagine how
yes, you can.
keys might conflict with each other. Yep.
If you're following along and you were worried about that, because I a little bit was, now you know.
Yes.
Oh my goodness. All right.
So that's our kind of correctness guarantee. There's also I said we'll set aside the issue of flushing and committing and the actual mechanisms that Kafka uses to guarantee the correctness and the exactly once delivery and all that sort of stuff.
You had all those problems also to solve or defer.
Yes, exactly. Yeah. So kind of the fundamental problem there is that Kafka uses offset commits to track what has been processed and what hasn't, and that is done per partition. So if I commit offset 5, that means that I have finished processing fully every record up to offset 5.
Up to 5 in this partition, right. Yeah.
Which means that if we want to kind of maintain these same correctness and processing guarantees that Kafka offers sort of natively in Kafka streams by being built on top of Kafka, we had to make sure that when an offset was committed, every single record that was every single record that existed before that offset has been processed.
Okay.
Which is hard to do because you have a thread pool and everything is working in parallel, and you might have Kafka streams sort of trigger or call for a commit to happen while you have a bunch of these threads off processing different records.
Things in flight, and you're like not going to be able to do that commit. Yeah.
Exactly. Yeah. So that sort of the fundamental fix there, right, is pretty obvious, which is just before you commit, you want to wait for everything that's in flight to finish up.
Which is fine because you kind of, when and how often and everything you commit, and that's a tunable thing, but you do sort of wait around to do that. And so asking that process to be like, actually just wait a second longer because we're doing something.
Exactly. It's kind of just like a checkpoint. And the fundamentally like challenging part there is more just how do we do this and how do we hook into the commit? Because in Kafka, in open source Kafka streams, it's obvious everything, the commit is a call from Apache that says, finish up what you're doing and then stop, and we're going to commit everything and wait before we move on.
Right.
But of course, our thread pools are just kind of off to the side. They don't really have a direct line of communication to Kafka streams because, of course, we have built this outside of Kafka streams or on top of it. So that was another big challenge. Luckily, we knew a little bit about the kind of fundamental implementation of these sort of offset commit and other protocols.
Yes, because you're all people who are deeply aware of the underlying stuff. So you built some of it. Yeah.
Yeah. So the solution presented itself pretty quickly, which is rather just more hijacking. We injected our own version of the Kafka clients, so we'd have our own custom version of the Kafka consumer and the Kafka producer. Now I say that as if it's a big deal. Really, they were just wrappers around the sort of default Kafka producer and consumer client.
Okay.
But what it did was it would intercept any call to commit or flush or things like that, and
wait on the appropriate synchronized things.
Exactly.
Doesn't that require a change to the client libraries on the client side?
Fortunately, Kafka Streams has thought about this before, and it already has a Kafka client supplier config, basically, that you can use to inject your own clients.
Okay. So config, fully qualified class name, jar file lying around.
Something like that, yeah.
And you're good.
Yep.
Okay.
So that part, was fairly straightforward in the end. And basically, just by waiting to finish up all the in-flight records until we commit, we get all of the same correctness and processing guarantees that Kafka offers, which is pretty nice.
Pretty great. It's fascinating with this question of what's the most interesting problem you've solved, just the different kinds of answers people take to that. This has been a great deep dive into how this stuff works. It's a really, really interesting problem, and I appreciate you taking us through all of it.
Yeah, thanks.
You bet. My guest today has been Sophie Blee Goldman. Sophie, thanks for being a part of Confluent Developer.
Thank you.